Sample problem number 6, internal force convection. So for this problem, it is actually similar with problem number 5. It's just that here we have water instead of oil flowing at a volumetric rate of 0.2 feet cube per second in a pipe that is 2 inches in diameter and 200 feet long. So the properties of water at 60 degrees Fahrenheit, which is the entrance temperature of the water, are also given, as you can see. So we will determine the pressure drop through the 200 feet long section of this pipe. So these are our assumptions. The flow is steady and incompressible. The entrance effects are negligible. So the flow is already fully developed in this particular section of the pipe. The pipe involves no components like bends, valves, and connectors. The piping section involves no work devices such as a pump or a turbine that would eventually add more heat or decrease heat. So the properties are already given for this particular water. So we have density, and then we also have the viscosity. So we just divide it by 38,600, convert hour to second, so we have pound mass per feet second. So the pressure drop formula is already familiar to us, and this is given as this. Now looking at this equation, we already have L, that is 200 feet. Diameter is also given, that's 2 inch. Just convert this later on to feet. And the density is already given also. The volume, the velocity. So we don't have the velocity, but we have volume flow rate. So of course we already know that volume flow rate is equals to cross-sectional area times the velocity. So we can always solve for the velocity using this equation. So if you're going to look at it, we don't have the friction factor. So first, to determine the friction factor, you need to determine what type of flow is this. Is this laminar or turbulent? So to determine that, solve first Reynolds number. So Reynolds number is given as this equation. So for the velocity, again, we can solve that by rearranging the volume flow rate equation. So the velocity is now volume flow rate divided by area of the cross section. Then substituting this value here, that's why we have this one. So that's why we have volume flow rate for the velocity. Volume flow rate divided by the area of the cross section, pi over 4 d squared. We convert the diameter to inch to feet. So 2 over 12, so it's now feet. So that's why we have 9.167 feet per second. So instead of, we cannot use this, it's volume flow rate, we will use this, 9.167 feet per second. So therefore our Reynolds numbers by this equation is 126,427.4. So 126,427.4. So this is greater than 10,000. Therefore, this one is turbulent. So this is our criteria. So if it is less than 2,300, that is laminar. If it is greater than 10,000, that is turbulent. If it is between, then transitional flow. So for Reynolds number greater than 10,000, the flow is turbulent. We can solve for the friction factor using this formula in slide number 32. So in slide number 32, the friction factor in turbulent flow for smooth tubes. So again, the Reynolds number is greater than 10,000 for tubes. So we can use this formula. 0.79 ln 0.79 ln of Re minus 1.64 to the power of negative 2. So we already know that our Re is 126,724. So just substitute the value of RE here, then we can solve for the friction factor. Take note, this is to the power of negative 2. So to give you another way of solving for the friction factor if you do not want to use this equation. So if you're going to use this equation, the value that you will get is 0.79 ln of RE minus 1.64, the answer to the power of negative 2. So approximately our F should be 0.01713. So if you will use this formula, but we have another way also of solving for RE. So depende kung ano yung choice mo. So for RE, for F, we can also use the Colebrook equation. So this is more complicated than that one, but this one is more. The good thing about this one is it actually considers the friction factor data for transition and turbulent flow. This one actually is dependent on the relative roughness, but for the problem that we have, we will assume it to be smooth. So for a stainless steel, so the given is actually a stainless steel pipe. The relative roughness, the roughness is 0.000007. So for stainless steel, this one is a stainless steel. So you need to determine the material first and then look at this table. So if it is feet or in mm. For this problem, we will use feet. And let us try to compare with our result. So with using the first equation, we actually have it 0.0173. How about the Colebrook equation? So the different is there is actually an iteration here because the square root of F appears on both sides of the equation. So the relative roughness is approximately the roughness, which is 0.0007, that's E, divided by the diameter in feet, 2/12. So the relative roughness is 4.2 times 10 to negative 5. Substitute this value here, and then you can shift solve to find the value of F. Then substitute also the Reynolds number. So again, we got the roughness here for stainless steel. So solving for F using shift solve in calculator, the value is actually 0.0174. So it's actually almost the same. So you can use the first equation, just assume that the pipe is smooth, or you can use this equation and then there's no assumption needed. It's just that the roughness is computed using the material for the material. So that's why we have substituting for the pressure drop in our equation, and then using the conversion factor, the value for delta P or the pressure drop in PSI is 11.8.